Okay, that's working. All right, so just a reminder of the week 2 goals that by Thursday that I want to see that each of you has made at least one commit to your repo so that I see that you're busy committing. I want to again see that code builds on the command line, including Javadoc and TextStyle. Look over your issues. There were a couple of teams who did a super job with the issues, and it was like 10 or 12 kind of smallish issues, and it was clear that they knew how to assign the work. There was another team where they had one issue, and the issue was basically finish the project, right? And so we're going to be looking at a bunch of issues on Thursday, and so when I look at an issue, I want to know, can it be done in a small period of time? And I'm arbitrarily saying at most 3 days. At most 2 days would be better. And so can it be done in a short amount of time, and is a single person assigned to it? So go through all of your issues and see, is it short, and is there a single responsible person? And so put in as many of these issues as you can for the things that you now know need to be done. So everything that you now know that needs to be done, there should be an issue for it. Does that get you to conclusion? Then you have a complete map of your entire project. That's great. And if not, let's go next week. So I want to see that each team member has closed at least one issue, so that I know, number one, that you know how to close issues, and number two, that all team members are involved. So if for whatever reason in your team it turns out that there's one person who just can't go with the flow and just can't do anything in a reasonable amount of time, this is the time when we want to know, so that we know how to work around it. And of course, you continue with your individual report. And what I want that you do is that when you closed an issue, you put the number of that issue into your weekly report. If you close 3 issues, then you can put those 3 numbers into your weekly report. And that way I can see that you're busy closing these issues. And if I see a project in which issues are busily being closed, then that smells like progress. If I see a project where people have no issues, then that's probably less progress. And so, as you see, I really want to get these things to move along steadily at a rapid clip, because if I don't do that, what's going to happen with a whole bunch of these teams, they're going to do the heroic effort the last weekend before it's due mode. And all of these projects are simple enough that you can actually do them that way, provided you make sure that only one person on the team does all the work and just plows through it. But we learn nothing from that, so I really want to see that steady progress. I don't want people to learn that the best way to do teamwork is to tranquilize all the other people on the team and just do it yourself, because that works fine for a small project, but it clearly does not scale up for something larger. All right, so on to today's lecture. So now the next several lectures are a whole bunch of fiddly stuff that's all important. So I'm going to be doing a half a lecture, a half a lab. Let's hope this is all going to work out. Yeah. So I'll start with the slides for the book. All right, so we'll get right into it. So what's a type? A type is something that it has a name, it has a set of values, and the operations that apply to the values. That all sounds crazily abstract. So you can think of a type as something that's like a class gives you a type. There's something that you can do when you have an object of a class, like over here. I have an employee object, and I try to call the clear method on it. Well, that's going to fail because E doesn't have a clear, and that is something that has to do with the type system. So the employee being a class is a type, there are certain operations that you can do, namely all of the methods that are defined in the class or one of its superclasses. So this kind of error here is found out at compile time. There are also type checks that are found out at runtime. So here we have an E that is null, and then we try to call set salary on it. The compiler doesn't find this kind of error because it's legal to store null in an employee, but it is not legal to invoke a method on null. So some type errors are found at compile time, some type errors are found at runtime. So what types do we have in Java? These are all of the types that are in Java. So there are the 8 primitive types that are an unfortunate exception because at the time that the Java virtual machine was first built, it was felt that the only way to handle them efficiently is to give them all separate special types. Now we know that had we not done that, we would have been able to build much more efficient virtual machines, but at the time that was not understood. You have what's called reference types. There are 3 kinds of reference types: class types, interface types, and array types. And then there is the null type. Trivia fact of the day, void is not a type. It's just an indicator of an absence of a type. There are programming languages where the equivalent of void is a type, but not in Java. So, when we look at these types here, you can see all of the various examples. In the interest of time, I'm just going to go through this. This is a primitive type. Rectangle here is a class type. Shape is a reference type. And these 2 here are both array types. Now, what you've just seen are the types that you can have for variables, parameters, return types, and so on. When you have a value, it's actually a little bit simpler. Then you can, of course, have values of primitive types. You can have references to objects or arrays. You can have null. The one thing that you can't have is you cannot have a value of an interface types. An interface cannot be instantiated. So you can also not have a reference to an abstract class. So I should see a reference to an object of a concrete class, one that's not abstract. Those are the only values that you can have in Java. This is very nice, actually. It's a very simple type system, unlike some languages that are really quite complex. For example, in C++, you have other types, right? You have pointers. You have pointers to functions. So those are all quite complicated types, and you don't have those in Java. Another trivia fact is that there are no types in Java for lambda expressions. Lambda expressions are immediately converted to objects of some type that implements that functional interface. So one of the beauties of Java is that you have a pretty simple type system. So here, we'll look at the types again. This is an instance of a primitive type of int. This is an instance of a class type. What about hello? It's also a class type, right? Java.lang.string. Here we have an instance of an array type. Notice that it's written as an anonymous array. And null is an instance of the null type, the only instance there. And that's common for object-oriented languages, of course. There is a subtype relationship. We say that some type is a subtype of another type, and there's a whole bunch of rules. So let's look at the rules. So if S and T are the same type, then one is a subtype of the other. If you have 2 classes, and T is a superclass of S, then S is a subclass of T. So a direct or indirect superclass means that there is some chain that says that S extends something, S extends something, extends T. Same thing, if you have an interface type that's listed in one of the implementation clauses, then you have a subtype relationship. Same thing if you have 2 interfaces. One interface can extend another interface. Now it gets a little bit more complex, so let me give an example for that. Oh yes, it's not very common, but it's legal. So read it up in chapter 4, I think. There's a contrived example there. So let's say I have a class employee array and I have a class manager array. Then which of them is a subtype of which? Is employee array a subtype of manager array, or is manager array a subtype of employee? Yes, so manager is a subtype of employee, or employee is the supertype, so this here is this supertype, and this one is the subtype. So if you have an array of managers, then that can be used wherever an array of employees is expected. Remember that that at first sounds like the most logical thing ever, right? One manager is a subtype of an employee, so why not the same thing for arrays? But it turns out to have somewhat surprising and possibly even disastrous ramifications. Everything is a subtype of object except for primitive types. Also not nice. So int is not a subtype of object. Everything else that's not a primitive type is a subtype of object. Now, amusingly, and we'll come into clonable and serializable in next lecture, every array type is automatically clonable and serializable. And finally, the null type is a subtype of every non-primitive type, every reference type. So everything that is a reference can be set to null, which also not necessarily the most wonderful thing. All right, so you can look at these things, but they're all pretty straightforward and academic at this point. So now on to the situation with array types. So here, shape is an interface. It's a supertype of rectangle because rectangle implements the shape interface. And so therefore, a rectangle array is also a subtype of a shape array. So let's say I have an array of 10 rectangles. Let's just visualize you have these 10 rectangles sitting there, and now I'm saying shape array S equals R. Is that legal? Sure, that's exactly what it means for shape array to be a supertype of rectangle array. If I have a rectangle array, it's also a shape array, and I can put it in this variable. All right, so now R and S, of course, are references to the same array. So here's R, here's S, and they both point to the same array that has 10 rectangle objects in it. Now look at this assignment. I say S bracket 0 is new polygon. Will it compile? Let's see, what's the type of S? It's a shape. What's the type of S, sorry, the shape array. What's the type of S bracket 0? It's a shape. What's the type of the right-hand side? New polygon. It's a polygon. Is a polygon a shape? Yes, it is. So there is a class Java AWT polygon, and it implements the shape interface. So now we're going to have here, instead of putting a reference to a rectangle, we're putting a reference to a polygon. This is actually very bad, because now when you look at R bracket 0, what is it? It's a polygon, but what's R? It's an array of rectangles. So if I now call a rectangle-only method, like get center X or such a thing, that the polygon doesn't have, what's supposed to happen? Is your keyboard going to melt into a puddle of plastic when you run something like this? No, right? Somewhere now there must be some runtime error message. And so the runtime error message actually happens at this line. When this line gets executed, then the array throws an array store exception. So here's what happens. When you have an array object, So, is that undo? Okay, we'll forget that. So when an array is created, like this array R here, at this point here, you think it's just an array with 10 slots. At the beginning, they're all null, of course. But it's more than that. This array remembers what it is. It remembers that it's an array of rectangle. So it knows what it is. And then when one stores anything in it through this other assignment, we now have S also pointing to it, but it's still an array of rectangles. When you now issue S bracket 0 equals, and one tries to put something in there, at runtime, the virtual machine looks at the type of the array, which the array remembers, looks at the type of this thing, and if they don't match, then it throws an array store exception. This is a burden on the runtime. The runtime has to make an extra check. Ideally, the idea of compile time typing is to keep the runtime free from making extra checks, but in this situation, it has to make it. So here, the Java designers, by saying that an array of subtypes is a subtype of an array of supertypes, by making this rule, they chose programmer convenience over compile time safety. They said, we'd rather have it easy on the programmer, and if once in a while there is an exception, we'll just deal with it. That's a trade-off that they made. And when we'll come to generics later, we'll see that there they made a different trade-off. And so at least it is somewhat confusing that you have that situation. All right, so that's the array store architecture. Yeah.
So obviously in the background, remember somehow they must put like a header or something in the array that says, hey, I'm this type.
That's exactly what it is.
So wouldn't it be easier for the Java compiler people to not put that check in there?
Well, but that would be unsound. If you have
Yeah, or you're right.
the easiest thing to do
They have to.
would be to forbid the conversion.
Yeah.
The easiest thing to do would be to say it does not actually make any sense that an array of rectangles is an array of shapes.
I guess it doesn't generate a compile time error because that would be more work.
Yeah, that was a Java thing. In other programming languages, in every other compile time checked programming language that I can think of, other than Java, it just wouldn't compile. Because that's the sound thing to do. So in Java they said, we'll make it a little bit more fluid, but we'll check that at runtime, and they felt that that was good enough. You can go either way, whether that's a good thing or not. So, the icky thing, when Java first was created, like I said, there was this need to make primitive types more efficient, but then you still need to be able to treat them as objects in some situations. For example, when you have an array list of numbers. And so they make these wrapper classes. As you know, there is a wrapper for each of the 8 primitive types. And then there is this oddity that you can box and unbox automatically, as it's called. So if you look at the line here, for example, we have an array list of integers. Not an array, but an array list. And so now I'm putting in an int and not an integer. 13 is an int. And then behind the scenes, the int gets converted into a new integer of 13. That's called auto-boxing, even though auto-wrapping might have been a better name. Conversely, when you call the get method, then you get an integer object back. If you assign it to an int, then it gets automatically unboxed by calling whatever the method is to get the int out. So that means you almost never have to worry about the difference between int primitive type objects, or primitive type values, and integer objects. You can assign one to the other. There's only a couple of things where you do have to worry about them. Number one is an integer can, of course, be assigned any int, but it can also be null. And so if it happens to be null, and then you say int n equals that integer, then you get a null pointer, etc. So that's a subtle difference. The other subtle difference is that equality works different, as we'll see when we talk about equality in just a few minutes. There are enumerator types. Now, if you pay careful attention at the previous slide, I told you that all of the types in Java are classes or interfaces or whatever. I'm now pulling these enumerator types out of the hat. Well, it turns out when you say enum and then something, you're automatically building a class. So an enumerated type is a class type. It's just a special kind of type. So here I'm saying that size is a type with exactly 3 values, small, medium, and large. And then I can use size as a type, like with any other type. And so I can declare a variable of that type, and size.medium is how you reference the medium constant in here. And so that's something that you should just always do instead of using like integer constants. Yeah?
Is it, in most other languages, that would also be interpreted as an integer? Is that not the case?
No, it's not the case. So most other languages means C and C++.
Yeah.
I think those are the only 2 languages that, well, that's not a language. So I have no idea about Visual Basic. So the beauty of using an enum is that it's not an int. And that way, if it was an int, you could by accident say things like image size plus plus. And then that would get you in trouble if you were already at large.
Yeah.
Which is what people do in C and C++ certainly on a regular basis. So these are not integers. You're guaranteed that image size is either small or medium or large, and never anything else. Except I just lied. What else can it be? No, unfortunately. So unfortunately, an enumerated type instance can also be null. So it can be 4 values, null, small, medium, or large. So as you can see, it would be kind of nice if the Java type system had a way of saying, I don't ever want this thing to be null. And it's something that every once in a while someone says, we should add non-nullable types to Java. And they haven't done that, but you see other Java-like programming languages that have embraced that concept. Okay, I don't want to talk about type-safe enumerations because that's old. There are a few ways where you can find out what the type of an object is. So if you have variable e and you want to know, is it a shape? Then you use the instance of operator that you've already seen. And that's kind of commonly done before a cast. So that way you know that the cast is safe. E really is a shape. You don't really know what kind of shape it is. Shape is an interface. So whatever E is, it surely isn't actually a shape. It is an instance of some subtype of shape. But you know that the cast is safe. Another trivia fact, what if E is null? If E is null, then instance of does not throw an exception, but instead it simply says it's false. Null is not an instance of any shape. And that's convenient because once in a while you have a reference that might be null. In that case, you surely don't want to cast it, then you don't want to use it, and it gets automatically rejected. If you want to know exactly what the type of an object is, then you have to ask it, and you have to say, get class. What you get back is an object of some other type. That type is called class. So e.getClass gives you the class of E. In this case, it gives you a class that describes Java awt.rectangle. There's 2 other ways of getting class objects other than asking an object. You can call class.forName, and then you just put in the fully qualified name in there, and then you get the class object that describes that class. Or more conveniently, you can call the name of a class .class, and then as long as you already imported rectangle, you don't have to put in the fully qualified name. So in all of these 3 ways, you get one of these class objects that describes what a class is, and we'll see much more about that in a week or so. Now, class here is unfortunately not a very good name of this type because int.class is legal, and it describes a primitive type. Void.class is legal. Shape.class is legal, and shape is an interface. So maybe type might have been a better name. So it's a type descriptor, really, that can describe classes, interfaces, primitive types, and even that non-type void. All right, I don't want to go into this. So let's find out, see, if we have an E, and now we want to know, is it a rectangle and nothing else, then this test here is good. We say get the class and check is it the same as the class of rectangle. Whereas if we called instance of, it could have been a subclass of rectangle. So you use instance of whenever you want to check for a class or one of the subclasses. You use .get class equal. If you want to check for that class and only that class. And you'll soon see an example of why we want to do that. Notice that here we can use equals because there's a unique rectangle.class descriptor in the virtual machine. So, if you want to talk about array types, I guess that's really quick. So suppose you have an array, A, and now you call a.get class. That's perfectly legal. You get the descriptor that describes, in this case, an array of doubles. We can ask if it's an array type by calling c.isArray. Then it says, yes, I am an array type. Then you can ask, what do you contain? And then you get the component type. And that, in this case, is double. Now, weirdly enough, when you call getName on it, let me just demo that because I think that'll be clearer. Let's see, how do I make the font bigger? Does anyone know how to change the font? Can I just... Oh yeah, okay. Yeah, the obvious thing one. Oh, come on. Okay, I'm not going to demo it then. When you call getName on an array type, you get strange looking types. You get bracket D for a double array, and you get, I have a two-dimensional array of strings, and you get two brackets followed by double length string followed by a semicolon. And you will see those once in a while, namely when you call toString on an array. Did you ever notice that when you call toString on an array, that you get a weirdo thing like that followed by the hash code of the array, just some bunch of hexadecimal numbers. All of this is because 20 years ago, that's how these things were represented inside the virtual machine. And for some reason, these implementation details leaked out, and then they never dared to change them for backwards compatibility. All right, so on to the most important part of today's lecture, the class object. All classes extend object. So object is a subtype, really, of every other reference type. Whenever you have anything at all, you can store it in an object. Why would you want to do that? Because it enables you to write some very generic, very general kind of code. Object does have a few methods. The ones that we're going to be talking about are the ones that you see here. We're going to be doing clone on Thursday, but today, well, I assume that you know toString. Today we'll talk about equals and hash code in some detail. And this may be repetition for some of you, but I think it doesn't hurt to see it one more time. So I don't want to talk about toString. I want to talk about equals. So equals is super important, and it's very common to get equals wrong. So equals tests whether two objects have the same contents. It's possible for two objects to be at different locations, but still have the same contents as you can imagine. Like I can construct a rectangle, and then I construct another rectangle object. If they both happen to have the same location, then they will be equal objects. So the equal symbol tests for whether the location is the same, but not whether the objects are the same. So again, to have my rectangle example here. So I could have a rectangle that has 5, 10, 20, 30 for x, y, width, and height. And I could have another rectangle that happens to have the same contents. And if this one is R1 and this one is R2, then it's true that R1 equals R2, but R1 is not the same as R2 because they refer to different objects. So the equal is, of course, very easy for the Java virtual machine to resolve. It just needs to look at where these things are located in memory. The equals is not something that the virtual machine can do in general by itself, because in this particular simple case, yeah, maybe it could look and see if all of the 4 instance variables are the same. But there are other situations that you can imagine where the internal representation is more complicated. Remember those dates, so those day classes that we had at one point, where we had that day 3 version, where the representation was ambiguous. It depended on whether you most recently used the Julian or the day month year representation. So you could have 2 things that represents the exact same day, but just because of the way that the value was computed, one of them might have had this flag set one way or the other. So simply comparing the internal structure of the object is not good enough. So the only way to compute equals is to make the classes themselves be responsible for it. And so we'll learn in a minute on how to do that with all the subtleties that are required. So, as an example where equals is used, I've copied this code here straight from the Java source code for index of ArrayList. So ArrayList.indexOf looks like this. It first checks whether the element is null, the one that we're looking for, and then it looks at where it finds null. But in the normal case, where it's not null, then it goes through all of the elements in the element data array, which is where the ArrayList stores the element, and then it checks whether element, the one that we're looking for, whether that equals element data. So you can see that if you mess up the implementation of equals, then index_of will not find the element, or it might find the wrong element. If you defined equals to always return true, then index_of will just cease to function correctly. And that's not just index_of, there must be hundreds of methods in the Java library that rely on the fact that you, the programmer of every class, have implemented equals correctly. Where correctly, it really depends on whatever it is that you want to do with it. So, a common way of overriding equals is to compare all fields. Not the only one, but that's kind of the most straightforward one. So that's what I'm doing over here. I'm having my employee class. I want to find out when are 2 employees equal to another. First of all, notice that equals has a parameter of type object here and not employee. Why? Where did it come from? Where's equals actually first defined? In object, right? In object, there's a method that says public class object, public boolean equals, then it has no choice. It has to say object. So that means that that equals is willing to compare an employee with any other object and not just with other employees. So we'll deal with that wrinkle in a minute. But right now, let's assume that an employee came in, so we cast it as an employee. And then we check, are the names the same? And are the salaries the same? And if so, then we return true. Otherwise, this and expression will return false. So notice that you need to do this cast, because you always get an object. And when you compare the fields, if the fields are themselves objects, you use their equals, like here we use the equals for strings. And if they're primitive types, then you compare them by using equal equal. So, am I actually saying this? Hang on. Yes, I say that in a few times. So, now, what about a subclass? You have a subclass manager. And so here I compare 2 managers with each other. And I first say if the employee parts are the same, then I can go on and compare the subclass fields, which is what I'm doing here. So that seems easy enough. You need to refer to the superclass implementation of equals to look at the superclass portion of the objects. Now, this was a very simple idea of comparing equality. It's not always as simple. I've taken this here from the java.util.abstract set implementation straight from the Java library. So this is how to compare two sets. Now, when you compare two sets, they could have the elements in different order, but they still need to be the same. So here I can't just look at all of the elements in the set one by one and see if they're equal. Instead, let's see what they do here. They check, well, this is an interesting little efficiency here. They check whether it happens that the thing that you're comparing the set with is the same as this. This happens surprisingly often in practice, and it's just an optimization. Say if they're the same object, I don't even have to look inside. Of course they're equal. Over here, then they check whether O isn't even a set. And if so, they say, well, then they can't possibly be equal. Otherwise, interestingly enough, they don't cast O into a set, but in a collection here. They could have done a set, I think it would have been cleaner. And now they check, are the sizes different? If the sizes are different, then they can't be the same set. But now if the sizes are the same, then they can call a different method called contains all. So if you have two sets of the same size, and one contains all of the elements of the other, where contains all does all the heavy lifting to iterate through what the one set and see what the other one contains at all, then they must be the same. So, what if you do nothing at all? Then you inherit object.equals. What object.equals does is, because it can do nothing else, it simply checks whether the objects are identical, and that's what it returns. So if you don't override equals, there is an equals method, and it does this default action. Now, you're free to override equals any way you want that makes sense for you. For sets, it was done differently than for employees, for example. Or not to override it at all, if you're happy to say two objects are considered as equal only when they're considered as identical. And the latter is not a totally unreasonable thing to do. For example, there's a class like output stream does not override equals. What does it really mean for two output streams to be equal to another? That they will always have the same values? They say, we're not even going to get into that. We'll only consider two identical output streams to be equal. And that means if you ever had an array list of output streams and you called index off on it, then you would only find the things by reference. But when is the last time you had an array of output streams and called index off? So it's not a big problem. So, like I say, you can do anything you want, but you're held to some simple rules that you're supposed to define equals so that x equals x is always true. So that x equals y is always the same thing as y dot equals x. And the reason for the second rule, for example, is so that a programmer does not have to scratch their head when they implement something like index off to ask, should I compare element data bracket I and ln, or should I compare lm and element data bracket I? The order shouldn't matter. And finally, if x equals y and y equals z, then surely x must equal z. Right? That's what's called the transitivity relationship. So in Math 42, you had these three relationships, and something that fulfilled all of these was called an equivalence relation. So in other words, equals must be an equivalence relation. And finally, when you call x dot equals null, for whatever reason, that's how they said it, it must return false. Clearly some amount of muddle-headedness in here from the point of the Java designers, because what is null dot equals x? Yeah, that throws a null pointer exception, right? So it would have been more logical and more consistent if they would have forced you to make x equals null also throw a null pointer exception. Why didn't they do it? I don't know. It seemed like a good idea at the time. So in general, with these things, consistency is pretty good as we've learned. Anyway, that's what the rules are that are actually published if you look up object.equals. So that means the employee.equals that I've just shown you, this very simple one here. Where is it here? It doesn't quite follow these rules, because what happens with this one here, if other object is null, then here everything is still okay. The cast will go through, other will be null. But over here, then you'll dereference a null pointer. So that's simple. So we need to guard against that. And that's easy enough to do. You just add a test. And so you'll find that test in every equals method that's ever been written. So if other object is null, then. Now, what if other object is not an employee? Then, of course, we need to reject the test, because an employee should only be equal to something else that's also an employee, right? And now here's a common thing that when you look at a lot of implementations that you find on Stack Overflow, whatever, but the equals method, they commonly use this test. They commonly say, if not other object instance of employee, then they return false. And that sounds like it's a good test. In fact, it's good that you don't even have to check for null, because null is not an instance of anything. But it turns out to be the wrong test. So if anyone has ever taught you to make tests like that in the equals method, they haven't really read the fine print. The problem is symmetry. Let's say you have you have a manager and an employee. They have the same name and the same salary, but one of them is a manager. Then we would want to consider them to be different, because m.equals e is false, and therefore e.equals m should also be false. And the simplest way of getting yourself out of this bind is to say, whenever you write equals, you don't actually use it, but you call get class. Get class is not the same as other object of the get class, then they belong to different classes. There are some exceptions to this rule, but they are few and far between. So, here's then how to simply do it. So it's easy. You can easily follow these rules by putting in the check against null, the check for the same class. And for good measure, I throw in this first line in here. That's just an optimization. So it's not actually hard to write the perfect equals method. Okay, do I want to talk? Yes, I want to talk about hashing, but from the point of view that you know what hashing is, because you've all had data structures. So we're going to have a lab in a minute, and you know what? Let's just go for the lab. And so go ahead, find the lab, find a buddy, and get started with it, because we're going to not be having time to finish it. And then I'll draw the hashing picture while you set up your lab. There's only one picture that I need. Find the lab. Yeah, go to the CS151 homepage, and here we have a lab, lecture 20. Find a buddy. Do we all have buddies? You guys here? Okay. One of you in the last row needs to come to the first row. Okay, how about you come to the first row and sit yourself here with us, space, so you find a buddy. Just go and sit right there. Grab an empty chair. It's plenty. All right, so one of you codes, the other one types up the answers, and we'll just see how far we get. So we're going to define this class point. Well, you'll figure it out. What? Project.
little bit, yeah. It's a lot of size. So something is wrong with the equals message inside of the points. So explain why you're getting the points. Because you don't work in the equals message correctly.
Why is it not?
First line. Other updations.
We do know that's wrong, but don't hold me to shit. Yeah, I know he said that, but
This is the wrong answer. So correct.
but isn't it only the one way when you have different? Maybe that one two is supposed to be on the point.
Yes, the
So it's their own thing.
Oh, that sucks.
I forget how it says.
Good thing,
It's too. Somebody
Did you try learning it? Get
yeah, I tried.
still this is a full bunch of shit now. I said last time.
So how do you answer that last one?
So let's have a before we go on here, guys. Let's have a quick look at how a hash set works. Because polling the back row, it seems that not everyone is clear then. So here I have a picture of a hash set. So the way that a hash set works is that you have an array of pointers to nodes, and each node has a pointer to the next node, and we call this thing here, call them a chain of buckets for whatever reason. And so these ones are the ones that have the same hash code. So you compute the hash code, you have to reduce it modulo the table size, and then you look at, let's say that it happened to be that h is 79, and now we want to find out whether x is already in here. Now this is just a hash set of strings, but for us it's going to be a hash set of points. So then we're going to go through these buckets here one at a time, and each time we check whether the data equals, the data that's already in here equals the thing that we're looking for. If this were to be true, then of course we wouldn't put it again. And if we go through the entire thing and we don't find it, then I don't have room to write this up here, then one would make a new node and add it in here at the beginning or at the end, whatever. So that's the basic idea. So now in our case here, let's see what happens. So did we define equals correctly? So if you look at the definition of equals, is equals correct? Yes or no? Where is it here? I'm going to have to erase this. So what does equals do? It does the usual preamble kind of thing here, and then it checks whether x and the x and y values are equal. So it doesn't seem anything wrong with it. How many values are we inserting? Everyone got that right, I think. Then you figured out that here there's only 4 possible points, right? 0, 0, 0, 1, 1, 0, and 1, 1. So we should be getting a set of size 4. Why are we getting a set of size 100 or some really screwy number when this n was when n was 1,000?
We didn't implement the hash code mask.
All right, so that is why I wrote. So this is like a common interview question. And so that may well be the first thing that they want to hear on the interview, but the next thing they want to hear is, what actually happened? Why does it produce 100? Why did it produce a screwy number? So with the implementation that we had, where we didn't implement hash code, why did it produce 100?
Because the add method of the set use hash code to compare two objects.
And
if you don't implement the hash code method of your class, if your return super of hash code, then it's true.
And
so it will be like two different. The set will consider them different.
And ha! All right. So in the first example, we now had 100 points that were all put into 100 different buckets. Because imagine what happened when the 57th point came along. Yes, it was equal to one that was already there, but the hash code was computed. The hash code happened to be something. There was nothing in there. So because it wasn't found in this bucket, a new element was created. It just followed the code, right? Compute the hash code, look up the chain, empty. Couldn't find it, so it puts it in. The next one, compute the hash code. Hash codes are wildly scrambled. The next one is over here. Nothing in there, added in there. Compute the next one. Nothing in there, added in there. Happened 100 times. And so therefore, the count in the end was 100.
Less because
Why wasn't it 10,000 or a million or whatever with the next one?
Because we finally got collision.
Yes, because if you had 1,000 of them, it did happen once in a blue moon that two of them, A, were actually in the same bucket, and B, they actually happened to be. And so there's a non-zero chance for it. You can see the chance was small, but it did happen once in a while. And the two of you, when you both ran the program on different computers, you got actually slightly different answers. So because the hash codes are kind of random when they're just derived from the memory location. Okay, so that's the actual explanation that you would be, so on a job interview, they would expect you to, draw this picture, put on a node that gets in there, and just tell the story like that. Just draw the picture exactly what happens with the first one, with the second one, with the third one, and so on. That's what they would want to know. And so it's an important job interview skill because when you interview someone, you want to separate two classes of people. Let me find my slide again here. You want to find the people who say, because this and this and this is going on under the hood. They're the ones you want to hire. And you don't want to hire the people who say, because of rule X. Because if you have something that can be solved by rule-driven programming, where all you have to do is remember 20 rules, that's done elsewhere, right? That you outsource. So to separate the outsourcers from the ones that need to be done here, you really want to find the people who can peel layers of the onion and who can tell you what goes on under the hood. And so that's the sense of this assignment. So that I want you to understand what actually happens. Because something actually happens, right? The computer doesn't say, well, because the programmer didn't follow this rule, I'm going to give some random answer. Right? The computer does something, and so it's important that you understand what that something is. So in this case, what the computer did was, it was rational, it was just not what we want. So here the remedy is, of course, easy to implement the hash code. So in the next thing here, I'm giving you this point too, where I do just that. I give you a hash code, but no equals. And so run this program here, and then kind of same questions. Why are you getting the wrong answer? And that's going to be kind of pretty similar to the first one. And now more interestingly, now change n to 1,000. And then something very strange will happen. I don't want to know why. Okay, I think we have time, maybe, just barely time for that. And then the third one, we'll have to do some other time.
create a list, you add them, and then you use hash code of this list because they only have two of them. So it will give you the hash code.
Oh, so you're essentially creating the single array. That point represents a single array.
Yeah. Just add the whatever one needs to be over here. Just add that on.
So I guess it's the same thing because you're returning. You end up returning a hash code.
But for the 0, 0, the hash code would be 0. For 1, 0, 1. Yeah, there are two. So if two objects is equal, they must have same hash code. This is wrong because 1, 0, and 0, 1, their hash code are all yeah,
That doesn't really explain why they got split. Right?
All right. So what's different?
You implemented the hash code.
So now we implemented hash code. So the first the first point comes in. Where's it put? What's the hash code of the first point? Maybe 0, maybe 1, maybe 2. That's the only possibilities, right? Because the hash code of a point is the hash code of its x and the sum of the coordinates. So the first one gets put here. Let's say it's 0. The second one comes in. Where does it go? 1. Let's say one of them has some 2. Now the next one comes in. Where does it go? It has to be and go into one of these, right? Where's the next one go? Same thing, right? It has to go into one of these because these are the only possible hash codes. So why aren't they ever considered equal? Well, which equals method is it using? We didn't implement an equals.
So it's using the,
So it's using object.equals,
yeah.
and we can say for sure that equals will never return false. It'll always say that they're different. So they will never be considered equal. So if I run this with 1,000,000 points, no, sorry, with 1,000, yeah, with 1,000,000 points, right? 1,000 times 1,000 points. How many am I going to get? I'm going to get exactly 1,000,000. I'm not going to get 997,000 or so. It will be exactly 1,000,000 because equals will always be 100% false. The hash code will always be 0, 1, or 2, and that's the picture I'm getting. Did anyone run it? Have you run it with 1,000?
Yeah.
Is it done?
No.
Why isn't it done? Why is it so much slower than with this one here? How long do these lists get?
because by the time they get to, because it has to compare, that's a lot of comparisons.
In the end, one of them will have length 500,000 and the other ones will have length 250,000 each. Because it's twice as common to get the number 1 than it is to get 0 and 2. Right? So that apparently takes long enough to keep the computer busy for some time. Must say, I was surprised myself when I ran it that it took so long. You were thinking, it's a million points, how long can it take? It's a computer, for crying out loud. But it does take long enough for doing that. So you can see why this is a great interview question, right? If you ever need to hire someone and they can draw you those 2 pictures and explain what goes on, you just know that you have someone who actually knows not just how to regurgitate some rules, but who knows what goes on under the hood. All right, I'll leave it at that. We're not going to get to the other one, and I'll see you all on Thursday. And on Thursday, you guys are on the hook to give some presentations.